Ask a standard language model about your company's private financial report, and it will usually do one of two things: tell you it doesn't know, or worse, confidently guess based on unrelated training data. We solve this by building a Retrieval Augmented Generation pipeline, or RAG, using Python and LangGraph. By the end of this tutorial, you will build a custom AI assistant that searches strictly through your provided files to generate responses grounded in your specific documentation. To follow along, you need Python, your preferred code editor, a sample PDF or text document, and an active OpenAI API key. Instead of relying on general internet knowledge, this setup forces the AI to reference only your trusted data. You turn a generic model into a secure, domain-specific expert. Step 1 is securing our environment. We set the OpenAI API key as an environment variable immediately. This ensures our script can authenticate without hard-coding sensitive credentials. Next, we ingest the raw data. Our Load Documents function uses LangChain loaders to scan our local directory and convert raw PDFs and text files into a standardized document format. We cannot send an entire 50-page manual to an LLM at once. It exceeds the model's memory limit, known as the context window. We have to slice the document into smaller, overlapping chunks. We configure the text splitter to create blocks of exactly 1,000 characters, with a 200-character overlap between them. That overlap prevents us from accidentally cutting a crucial sentence in half. Execute the script. Your terminal will print out exactly how many chunks were successfully generated. Sizing these pieces correctly dictates the quality of the final output. Tightly focused chunks allow the system to perform highly precise searches. Now we convert that text into a format the AI can actually search. We initialize an embedding model, which translates our text chunks into mathematical vectors. We store all of these newly created vectors in a local face database. Think of this as the long-term memory for our application. Before going further, test the retrieval mechanism. Pass a sample question to the vector store and verify that it returns the correct document chunks in the terminal. Because we are matching mathematical vectors rather than raw text, the database finds information based on contextual meaning, skipping the rigid limitations of exact keyword matching. LangGraph operates on a state-based system. We define a RAG state dictionary to track exactly what data, the user's question, the retrieved context, and the final answer, flows from one step to the next. Next, we define the individual actions. We create a retrieval node that takes the user's question from the state, runs it against our vector store, and returns the top 3 most relevant chunks. Then we create the generation node. This node grabs that freshly retrieved context, injects it into a prompt template alongside the original question, and asks the LLM to generate an answer. By isolating these tasks into independent nodes, we turn passive data retrieval into a modular system where every step can be tracked and debugged. This diagram compares a traditional RAG setup with a stateful graph architecture. A traditional chain pushes data linearly. A LangGraph setup allows us to implement conditional routing, deciding on the fly which path the data should take. To build this structure, we initialize a state graph and register our retrieval and generation nodes into the workflow. We establish the operational flow by setting the retrieval node as the entry point and drawing a direct structural edge connecting it to the generation node. Graph routing gives you complete control over the logic. The pipeline upgrades to a robust application capable of handling complex decision-making. We execute the complete pipeline by calling the invoke method on our compiled graph and passing in a natural language question. The graph processes the query, routes it through retrieval and generation nodes, and returns a response based on evidence found in your source data. From here, you can add conditional logic, like having the graph automatically rewrite the user's question if the initial search returns poor results. Because every response is directly anchored to your specific vectors, the AI references your documentation rather than its training data. You now have the structural foundation required to build secure, reliable AI applications.